Hello, good morning, namaskaram. So today we are going to discuss with direct stiffness matrix. So this is a beam. This is a beam. This is a UDL loading. This is a point A. It's a point B and it's a point C. So it is UDL is loading at 16 kilonewton per meter. This is 16 kilonewton point load. This is a 5 meter distance, 5 meter distance. That portion is 3EI. That portion is 3EI. It is I. So let us discuss with the direct stiffness method. Steps are: first step is we have to calculate dk. So we have to calculate dk for fixed beam. Dk will be 0. For roller it will be 1. For this roller it will be 1. So dk will be 2. Dk will be 2. That means theta b and theta c. Here rotations will on theta b and theta c. So next step is we have to assign coordinates, element coordinates. That you have to split the beam in two portions, AB and BC. AB. In AB we have to assign coordinates, vertical reaction VA and moment will be theta A or MA. Here also vertical movement, vertical reaction VB and moment will be theta B. Here VB theta B, here VC theta C. That is called element coordinates. Now we have to assign global coordinates. Global coordinates means you have to assign the coordinates of the whole structure. This whole structure you have to assign the coordinates. So we will take here VA theta A. Here it will be VB theta B. Here it will be VC theta C. That's called global matrix. So next step is elemental stiffness matrix. We are denoting by the symbol K. K, we know the formula, 12EI by L cube minus 6EI by L cube. We have to remember this by heart. This formula, this matrix, we have to remember this. So we will take different spans. For AB span, for this AB span, we have to calculate elemental stiffness matrix. So elemental stiffness matrix here in this EI, in AB portion EI is 3I. I is 3I. So we will put here I value 3I and L cube is 10 meter. L cube is 10 meter. So here will be 10 meter cube. Here 6 3EI L square means 10 square. Here 12 3EI by L cube 10 cube. So on substituting the values we will get the values of K matrix of AB span. Here I is equal to 3I and L is equal to 10. So here we got the matrix, this for KAB. Now we will assign vertical reactions and rotations. Here it first coordinate is VA, then theta A, then VB, then theta B. It is like this. It is VA theta A, VB theta B for this span. So here we can also write VA theta A, VB theta B. After that we will calculate elemental matrix for span BC. BC is the same formula but we have to change the values here. Here it is EI. Oh, I will be here, I will be here, I value. And L cube is here 10. 5 plus 10. It is 10 cube. So after that we will get the values. After getting the values we will assign VB theta B, VC theta C and VB theta B, VC and theta C. After getting two values of elemental stiffness matrix and KAB and KBC, now we have to superimpose On superimposing the two matrix, we will get the values of this. How to make this matrix? I will show you how to make this. So we have to calculate K. K equals to EI. EI will be same here. Here it is also same. So we will calculate EI equals to, here first, where is the rotation? Theta A, theta B and theta C. Rotations will be there. Here also theta B and theta C. Rotations will be there. So how to get this matrix? We have to superimpose these two matrices. Let's check. Here, first element theta A and theta B and theta B. So we will check on first matrix KAB. KAB, we have to check theta B and theta C. Theta B is here. Theta B and theta B. This is column, this is row. Column to row, we have to check value of theta B and theta B. It is 1.2. So here theta B column, theta B row, here it will be 1.2. Now we have to calculate theta C and theta B. Theta C column, theta B row. Theta C, here it is not theta C in KAB matrix. Here it is not theta C. Now we will check here in second matrix K beta C. Theta C and theta B. Theta C and theta B, row and column, we will get this value 0.2. So we will write here 0.2. Now theta B column, theta C row. Check in the first matrix theta B column and theta C. Theta C is not here. Theta C is not here. Check in the second matrix. Here it will be theta B and theta C. Theta B, theta C. So here we will get 0.2, row column to row. Here it is 0.2. So we write here 0.2. Now theta C and theta C. In first matrix there is 0. Theta C and theta C 0. Now in second matrix, here it is theta C and theta C. Column, which is row, 0.4. So we write here 0.4. We got the matrix, elemental stiffness matrix. So next step is to calculate the fixed end moment and EJL, equivalent joint load. So we have beam given here. We will separate this into two elements, AB and BC. For AB span, it has UDL. It has UDL. So we have to calculate this end moments. Summation of fixed end moments. We have to calculate fixed end moments of AB span will be equals to minus WL square by 12. When we enter the value of W, I will show you. W is 16 into L square. L square is 10 square divided by 12. It will be 13133.33 kilonewton meter. So from this side it will be minus. It is an anti-clockwise direction, so we will take here minus. Like that, FEM of BA, this moment, B to A, it is formula is WL square by 12. That way again get the value of 133.33 kilonewton meter. So also we have to calculate reactions. Reaction is here RA and RB. How to calculate the reactions? Here it is UDL. So here will be WL by 2. Here WL by 2. Here also will be WL by 2. Reactions will be WL by 2. So W is 16. Load into distance is 10 divided by 2. We will get 80. Also RB 80. So for second span BC, you can see here second span BC, it is 16 kilonewton point load here. So I draw this 16 kilonewton. So fixed end moment of BC portion, the formula is minus WL by 8. That will be minus 16 into 10 by 8 equals to 20 kilonewton meter. From this side it is 20 kilonewton, and also from this side it will be 20 kilonewton. So RB and RC we have to calculate. RB formula is this for point load, W by 2. Here W by 2. W is 16 by 2, that will be 8. So RC will be also 8. Now we have to draw these reactions and fixed end moments on the beam. So we will take separately. It is A, it is B, this is B, and this is C. AB portion. For AB portion, we got from this side A to B how much? 133.33 kilonewton meter. So here we assign this, and here also 13.33. And also reactions RB and RA. RB and RA we calculated 80 and 80. So assign this 80 and 80. For second beam we calculated 20. Here also 20. Here also 20. 20 and 20. Now we have to calculate EJL. EJL, equivalent to joint load. So how we calculate that? Fixed beam cancels this moment and this reaction. So here there will be no this moment and reaction. So here we can write as simply fixed. And second load is, here it is 133.33 kilonewton meter in clockwise direction. Here it is anti-clockwise direction. So here it will be 133.33 minus 20. So it is 113.33 kilonewton meter. So that load, it is in clockwise direction. So bigger load is this. So that will be clockwise direction in what is that? 113.33. But we have to take in EGL, we have to take in reverse of this load. It is clockwise direction. So we will take here anti-clockwise direction. Here anti-clockwise direction. Here it is 20. Here we will take it anti-clockwise direction. So also reactions. Here it is 80. Here 8. So it will be 88. Here it is 8. So we will get the matrix of R. Here we have to take negative sign. Here also negative, because it is anti-clockwise direction. So we will get this matrix. Now fifth step is displacement matrix, which is equal to R equals to K inverse P. K we get. K we got here. Here you see K will got K equals to EI 1.6, 0.2, 0.2, 0.4. So we will place here K value and here P value. P value, it is R value. Simply it is R. We got this R value here. This value. So after multiplying this, how to take the inverse and multiplication, I will show you on the calculator. First, we have to calculate this K inverse and multiplication of R inverse. So you simply shift mode. Here it is matrix 6, sixth option. Here it is matrix A. So we have 2 cross 2 matrix. So 2 cross 2 is here 5. Then we will assign the values 1.6, 0.2, 0.2, 0.4. So we enter the values. Then press this on button here, on, then shift 4, then here option is data is 2. So we have to enter matrix B. So option 2. This matrix is 2 cross 1. So 2 cross 1 option is 6. Now enter the values. Minus 113.33. Second value is minus 20. So we enter the two values, matrix A and matrix B. Now press this on button, press shift 4, and here it will be matrix A option is 3. Matrix A option will be here. Then take the inverse matrix of A, matrix of K. So inverse into multiplication of matrix B. So here it will be matrix B, that is fourth option. Fourth. Now we will get the equals to value. We will get the values. Minus 68.88 here, minus 688.8. Then second value is minus 15, minus 15.55. So we got the values of R value. R. Here by 1 by E. Here it is E. So we will take this inverse. It will be 1 by E. Now final moments. Final moments. Here we will calculate Q equals to KAB RAB plus fixed end moment. So we will take separate beams, then we will calculate the reactions and the moments. So here Q will be equals to VA QA VB QB. Reaction of point A, moment at point A, reaction point at point B, moment at point B. So it is equals to KAB. KAB we got in step 3 here. KAB we got this value. So you have to write this value to here in this equation. So I enter the value into RAB. R we calculated here. R value we calculate here. It is theta B and theta C. So here it is R value. How to write these values? This 0 0 0 minus 68. Here it is 68. I will show you how. This is span AB. We assign coordinates VA QA. Here VB. Here QB. So for span AB, reaction A, we have to calculate rotations. There will be only rotations at B and C, not A and B. A because A is fixed here. A is here fixed here. So we have to calculate the rotations at B and C. So here VA will be 0, 0. Theta A will be 0. Theta A will be 0. VB, here it will be 0. But rotation we got from this R matrix, that is minus 68.88. So here it will be minus 68.88 plus this fixed end moments. So after calculating these two matrices, then we will get the value. For example, we got some value there. It is 4 cross 4 matrix. It is 4 cross 4 matrix, and also it is 4 cross 1 matrix. So the final matrix will be 4 cross 1. 4 cross 1 will be the final matrix plus fixed end moments. How to calculate the fixed end moments? I will show you how to calculate this FEM, fixed end moment. Fixed end moment we will get from here. So this is a portion AB. I will show you FEM. Here fixed end moments. First you have to write reaction, because we are taking here reaction first, then moment, reaction, moment. So like that. So here it will be 80. It is clockwise direction, so it will be 80. Then here it will be in negative, in anti-clockwise direction. We have to take negative value. It is 133.33. So it will be minus 133.33. So for this portion. Then for this portion, here it is 80 VB. VB is 80. Then here QB is 133.33, but in clockwise direction, so take it positive. 133.33. This is the fixed end moment for span AB portion. So we are calculating here for AB portion. So fixed end moment will be AB portion. After multiplication and this addition of fixed end moment, we will get the value of Q 92.38. One this value, this and this. It is VA, QA or MA moment. Moment and QA is same, rotation or moment. And VB and QB, MB. So after that, for span BC, Q2 is KBC into RBC plus FEM. So KBC we know in step 3. In step 3, elemental stiffness matrix, we will get this value. We will get this matrix. So you have to enter this value here KBC into RBC. What is this RBC? It is the displacement matrix here R. How to do this? This will be, I will show you. This is RBC. It is a portion BC. Here it will be VB. It is rotation QB. It is rotation reaction VC. It will be rotation QC. So here we have two unknowns, QB and QC. So here RBC, first value is VB, so that will be 0. Then second value, that is QB we calculated minus 68.88 in here, and this matrix R, it is QB and QC minus 68.88. then second that is VC is also 0. VC is 0 here. Then QC is minus 15.46. we calculate it here. So you have to take care of this. You must understand how it comes. So then plus fixed end moment we will calculate the portion for BC span. Fixed end moment will be first reaction 8, then minus 20, then 8, then 20. It is positive direction. So here 8 minus 20, 8, 20. So after multiplying and addition of these three matrix, we will get the matrix this VB, QB, VC, QC. So now we have to draw the bending moment diagram. How to calculate the bending moment diagram, I will show you. First you have to draw the beam, then we will calculate. We calculated here QA we calculated here, it is minus 174.62. so we have to assign this. We have to draw this on this portion that we calculated bending moment diagram. We called it bending moment diagram. That is 174.6. We take a point here. Then 8 point B. This is for AB portion. Portion BC. Here we got MB value, that is minus 50.681. so here we will take a point 50.681. then BC portion, for BC portion the value is 0. bending moment, the value moment, not bending moment, the value is 0 here. So this line join is this point, C point. It we called it A, we called it B, it's called it C. So join these 3 points. We got this bending moment diagram. So you have to also assign that UDL load is here and point load is here. Point load is 16 kilonewton. So you have to draw also the bending moment diagram of these two loads. For UDL load, the bending moment diagram value will be WL square by 8. WL square by 8 on when you apply this W and 8 is 10 meter. Value of W and L you will get 200, but that will be parabolic because it is a UDL. Then second, for this point load, it is 16 kilonewton. For 16 kilonewton, you have to draw the bending moment diagram. WL by 4, it will be a triangle. It will be a triangle. Yes, it will be a triangle. WL by 4. On applying the value of W and L, you will get the 40 kilonewton. 40 kilonewton meter value. So this was this direct stiffness matrix method. It is a simple beam. So I will show you other small things. For it is W. For calculating the fixed and moments, it is a simply supported beam. W is the load which is acting on a center. So for this point load, here fixed and moment will be WL by 8, but in negative, it is anti-clockwise direction. Here it will be clockwise direction. For a beam having different spans A and B, fixed and moment will be WAB square by L square here, WB A square by L square here. So for UDL, it will be WL square by 12, WL square by 12. So reaction will be WL by 2. Here also WL by 2. For this, it will be WL by 2, WL by 2. This is a fixed and moment. Now moments, simple moments we have to calculate. Here it is a different spans AB. That bending moment diagram will be a triangle with the value of WAB by L. For the same beam, but point load is at a distance of AA. That means it is acting on the center. So the value will be WL by 4. For UDL case, it will be WL square by 8. So I think you got the direct stiffness method. This is a very simple method. So you have to only concentrate on the steps. How to do the steps? First you have to calculate dk, then assign the element coordinates, then global coordinates. After that, then you have to assign elemental stiffness matrix K. You have to remember this formula. You have to remember this formula by heart. Then after applying the values of L and EI, then you will get this matrix AB. Then for BC span, you have to, but remember this is one thing, don't forget to write this here: VA QB VB QB VA QB VB QC. Don't forget. Then after that, after getting two values of matrix, then you have to superimpose. You have to superimpose in direct stiffness method. In stiffness, you will not superimpose. Only this step is in direct stiffness. So after superimposing, we got the values of K here. Then after that, fixed and moment and EJL. Simple. Then we got this R matrix. Then after that, step 5 displacement matrix here, K equals to K inverse R. So K inverse, we got the value here. After that, final moments, that will be KAB RAB plus fixed and moments. After getting for different two spans for AB and BC, if there are 3 spans, for example, if there are 1, 2, 3 spans, so you have to calculate for AB span, for BC span, for CD span, for 3 spans. Then after calculating for BC span, you will draw this bending moment diagram. Okay, thank you.